Well, hello everybody. Welcome back to Physical Science today. This is where we left off yesterday, and these are our electron transfer diagrams. And these are for ionic compounds. When an atom actually donates an electron, well, they say donate, but really the only reason why it moves from one atom to the next is because of the force of electricity. And if you look at these, and I'm sure you all did study this because we talked about it yesterday, all of our compounds that we put together were made up of things from this group in combination with that group, and then these things. Did you notice that? So when you did your worksheet, it was always blues combining with greens or something real close to that. Okay, so I need somebody to explain to me why that was. Sir?
The blues are losing electrons and the greens need to gain electrons.
Exactly right. The blues are losing electrons and the greens are gaining electrons. And so that's why they come together. Okay, so those are our ionic compounds, our salts. But then, and the reason why these guys gain is because they have that really strong attraction to electrons because of the size of the atom. And the reason why these lose is because they don't have a very strong attraction to their outside electrons because of the size of the atoms. So it's easy for these guys just to take one from these guys, and then they're both happy. But here's what we got to answer our question for today is, what happens if we get a compound between things that are over here? So, in other words, because you know what we breathe is
Oxygen.
oxygen, very good. And oxygen is a diatomic compound, which means that when it's elementally alone, you have two oxygens floating around together. So we need to figure out how that happens, how two oxygens go together. Because there isn't going to be one that's stronger than the other as far as the pull for electrons. Does that make sense? So like if I get two oxygens close to each other, they're not going to have different attractions to their valence electrons because they're the same size atoms, they have the same number of protons, the same number of electrons. So we need to figure out what's going to happen there. And if you remember in the beginning, we said that compounds are made by either transfer electrons or what was the other word we used? Sharing. Very good. Sharing electrons. So that's our topic of discussion most about the day. I just want to finish up with what we didn't actually write down yesterday. So one thing to kind of jump back to yesterday, clean up where we left off, was this right here. Okay, so if you want to take a second and put this into your notes, that would be good. Okay, so when ionic compounds transfer electrons, then the atoms or polyatomic ions become charged. And because of that plus or minus charge, then they have an attraction to each other, just like the opposite poles of magnets. So what happens then, for instance, to refresh your memory from yesterday, we know sodium is going to lose one electron to the chlorine and add to the chlorine's electrons. So then we get a sodium with the plus side, a chlorine with the negative side, that has an extra electron. And because of that, the sodium is attracted to the chlorine because they're opposite charges. That's a fundamental law of electricity. And so what happens with these salts, which is different than what we're about to talk about, the molecules, is we get big chunks. So we don't ever get just an NaCl piece. We don't get it down to an NaCl piece. Although we call that the formular unit, okay, or formular unit, which would be the simplest ratio of the ions in a compound. But we never get like an NaCl floating around together. Instead, what we get is a big crystal lattice here of positive and negatives. And it's, billions, trillions of particles all as one piece. Okay? And so we get this big crystal lattice formed, and that's the way all of our ionic compounds are. Now this is different than our covalent compounds. So our covalent compounds, we're going to get something that's called, well, before we go into that, because of the way this structure is, like look at this guy. How many negatives does it have around it? It's like locked into place. Or look at this guy. How many positives does it have around it? It's like locked into place. And because of that, then we have this high melting point and high boiling point. And we have a very strong bond because they're all locked into place. But when we do the sharing of the valence electrons, we get something a little different, and that is called the covalent bond. And so when you think of this word, covalent, you should be looking at the base. Valent is going to be valence electrons. The prefix, co, just like co-pilot, co-producer, they share the responsibilities. So these covalent bonds are sharing their valence electrons. Okay, so that's not in there, but you need to know that covalent bonds are sharing their valence electrons. Okay, so our notes are saying that's the most common bond. Most of these have lower melting point and boiling points. And that's because they're not locked into this crystal lattice. These things might have partial polarity, but they're not going to have an absolute positive and negative side to them that's going to lock it up into a crystal pattern. Okay, so that was a very good question about the brittleness. And Roger was wondering about if it's such a strong bond, then why is it brittle? And we kind of explained it in a way that it's a rigid bond. So it doesn't bend very much. And so if it doesn't bend, it breaks. You've heard that term before, right? So that's what that brittleness means. Is it's rigid, it can be really strong, but it can still break. Okay. So now we have to look a little bit further into these covalent bonds. Okay, here's a few more notes that you can write down, and then we'll explain those here in just a little bit. But the biggest thing I want you to think of right now is that these molecules are actually little units that are independent of each other. Where the ionic compounds, the units are all stuck into place because of the alternating positive and negative crystal lattice. Molecules are different that way. Here we go. Okay, so we're looking at, the word molecule. And this is what we call the smallest unit of a covalently bonded compound. Covalent, remember, they're sharing valent electrons, and they can be drawn in electron dot form, which is the assignment for today. I'm going to show you how to draw that. So yesterday we had to show transfer. Today we're going to show how we share them. This right here says that the shared electrons, they spend most of their time between the two nuclei that they're being shared among, okay? Now, sometimes, though, there's such a strong pull from one to the other that it won't happen that way. Like, if I have oxygen, oxygen has 8 protons, right? So, plus 8, and then there's a lot of electrons, or there's a lot of pull for electrons there. And if it gets bonded to a hydrogen, to 2 hydrogens, they only have plus 1 for a proton pull. So what happens with this then is the one electron that hydrogen brings with it to the bonding, and actually spends quite a bit of time around the oxygen. And remember, these things are going around really fast. I mean, they're all over the molecule. And so then what happens then is we get a partial negative bond on this side of the molecule, and then we get partial positive bonds or polarities on this side of the molecule. Okay, so even though this says that the electrons spend most of their time between the two nuclei, it kind of depends on how strong the pole is from each nuclei. Okay. Here's the big deal right here. The atom will share enough electrons to fulfill the octet or duet rule, or to fill its outer level. And when we say fill, that's actually not right, because, you know, we know the third sublevel can have more than 8 in it, right? And the fourth, fifth, and sixth. So really, you should change this on your notes to say, to fulfill the octet or duet rule. Okay, so here are some examples for you then. So these are examples of how I'm going to want you to show here. I'm going to show you some other techniques too, but for right now, so that you guys know that there's a sharing of valence electrons, I want you to draw the electrons that are being shared between the two atoms. So if you look at this first one right here, hydrogen, they each only have one valence electron, right? And I signify the sharing by having one from each. So use, X's and dots to show that, hey, one of the electrons is from one hydrogen, the other one's from the other. And this then would be the notation I want you to use for today's worksheet for the hydrogen bonds. Now, oxygen is oxygen has a double bond. This is called a single bond because they're sharing just 2 electrons. Oxygen has to share 4 electrons to fulfill the octet rule. Okay? So if you look at this, then I'm showing that, taking my dot diagrams that we've already done, but I'm drawing them in a way that shows that, hey, we got to show they're sharing 2 of them, or 2 sets of them. Okay, so how does this fulfill the octet rule? Because if you look at this, there's 1, 2, 3, 4, 5, 6, and then these count for that one too. So that's how the octet rule is fulfilled here, because the ones that are shared count for both atoms. And then on the other hand, on this side, then we have 1, 2, 3, 4, 5, 6, and these count too for that one. Because they're sharing, they can count them for their octet. Okay, so I'll give you a little bit to copy down these examples. Okay, so now that you got those examples written down, keeping in mind that we have different names for the bonds depending on how many pairs of electrons they're sharing. 1 pair is a single bond, 2 pairs is double, and 3 pairs being shared is called the triple bond. Look at this. It says double bond is harder to break than a single. Therefore, if something has a double bond, it's less reactive. Okay, diatomic molecules. This is not the first time that we've talked about diatomic molecules. So, you should already understand what it means. Di is 2, atom is atoms. So our diatomic molecules are 2 alike elements bonded together when elementally alone. So here are your diatomic molecules. We've been talking about these for a long time. We'll just take a look at our periodic chart here. Remember, diatomic molecules already marked on your periodic chart here, and these guys, right? So the upside down L plus hydrogen, which means when they're by themselves, they always come in sets of 2, they're covalently bonded. Okay. And I know you probably want to make sure you write this down. The polar molecule we already talked about here a little bit too. Okay, so this polar molecule part also we just talked about when I drew up the H2O, and I explained how the oxygen is so much stronger of a pole that the electrons spend more time around the oxygen than the hydrogen. But it's not so strong that it's considered an ionic compound. So it's somewhere in between the traditional, like, covalent, like absolute perfect sharing, and the transfer. Somewhere in between there is where we get these polar molecules. And that is why ice is so special, because of its partial polarity. And so when it forms its structure of ice, it's actually less dense than liquid water. Okay, so we're just going to look at a couple examples of how to draw these diagrams, and then I'll let you go on the worksheet. But the first thing you have to do is have your periodic chart out, because it's all about the valence electrons. Okay, so let's just say, for example, we're going to put a chlorine plus a chlorine together. Okay, so the first thing you want to do is draw your valence electrons for chlorine, which you all know is 7, right? Okay, so you want to make sure that you know this, and you can combine these steps. But by looking at this, how many do they have to share? Just one from each, right? So then the final answer, and you could do this right away if you can see it, would be this. Just showing that, hey, those two in the middle are being shared by both atoms. Does that make sense?
Yes.
Okay, so let's try another one. Let's try oxygen, should we? Or how about nitrogen? Or let's just try phosphorus. So phosphorus and phosphorus. So if we look at the covalent, or the valent electrons for phosphorus, we have 5, right? So we have 1, 2, 3, 4, 5. We have 1, 2, 3, 4, 5. Okay, now they each need how many?
3.
3 more. So that means they have to share how many? 3, because for every one they share, another one gets shared back to them. So all you got to do then is go P, P, and put 3 right in between them so you can see that they share, and then you can file the rest around. Okay? So that would be the covalent electron diagram for this molecule. You guys want to give it a try?
No.
Okay, well, let's try one more then here first. Let's try one that's a little more complex. Let's say we have, or maybe it's less complex. Let's say we have CH4. Okay? So, what you want to do is, well, you've got your H's over here, right? They have 1, and then we have our C over here. They have 4, right? So now H's, are they happy with, how many do they need to be happy?
4.
A hydrogen only needs 2, right? Yep. So if they can share this one and give another one back in return, then they're going to be happy. How many does carbon need? 4 more. So it has to share all 4 of those. Can you start to see how this is going to combine now?
Yes.
Yeah, so then our final is going to be like this. There, that hydrogen's happy. That hydrogen's happy. That hydrogen's happy. And that hydrogen's happy. So there's our final covalent diagram for CH4. Okay, hopefully this helps you guys, and hopefully you can do well on your assignment. Let's get started on that.